So this is the second part of my 3n+1 Collatz Conjecture, video. Essentially a follow-up video, continuation of my thoughts about the conjecture. I'm still working on a method to come up with a concept that's meant to try to disprove the conjecture, but it will essentially prove the conjecture, if that makes sense, right? A way to say that if this is true, then the conjecture is false, but that's only if this is true, you know what I mean? So I'm trying trying to prove the conjecture wrong, but more likely it will fail at doing so because of the nature of the one of infinity, and second, the Collatz conjecture itself, on how it functions with the understanding of infinity. Therefore, any method I come up with, or any method that is created to try to disprove the conjecture, will fail. Well, anyway, let's get to this video. To this idea. So first off, start with a quote. The Collatz conjecture will always go down to 1, but it has to try to go to infinity first. That's by me, my quote. So that's what I believe, that any number you choose and then punch into and then you apply the Collatz conjecture to will at some point try to go to infinity, the 3n+1 scenario, because there'll be an odd number. If you choose an odd number, it will automatically try to go towards infinity, but as soon as it reaches an even number, it will go back. It'll try to go back to 1, and every time an even number pops up within that process, it will always, it would drastically take steps back to 1. So that's the whole idea of the Collatz conjecture, is, if n is even, it would be divided by 2, which is huge steps back. So that's an important detail. So even though somebody did point out the idea that the number 3 is bigger than the number 2, but when it comes to division versus multiplication, if division happens more often than multiplication, then 2 is irrelevant, right? Because it will outnumber it eventually. Just going to throw in a little bit of my theory for the disproving of the conjecture, is the idea that if there's a realm within infinity, where there's a number, as soon as you pick it, it will, it'll be an odd number, obviously, right? You'll times it by 3 plus 1, and it should still be odd. And then you do it again, and it'll keep going odd, because all the numbers in that realm, they're all odd numbers. You will never land on an even number. You will never land on something that has an even number in it. That's the only way, in my mind, that you will never go down to 1, because you never hit an even number. And if you never reach an even number, you never divide by 2. Which means you will always just be multiplying by 3 plus 1, multiply by 3 plus 1 until, right, for infinite. Infinity. You just keep repeating that process over and over and over again, and the process never changed. you will go in one direction, never go the opposite. But the conjecture is designed to go one direction, and once it gets to a certain point where a variable changes, aka something going from a odd number going into an even number, then it reverses course. It tries to go back to 1, right? Every odd number is trying to go to infinity, every even number is trying to go to 1. So anytime you reach an even number, you always try to go back to 1. So the first part here, after the quote, you'll see that I put the conjecture, 3n+1. If it's even, divide the number that you choose by 2. Well, obviously it'll be an even number by 2, divided by 2. If it's an odd number, 3 times the odd number plus 1. Just so you can visualize the conjecture, obviously, while you're processing your ideas and theories and punching in numbers, coming up with types of numbers that could break the conjecture or fit well in the conjecture, whichever way you want to look at it. So you got to break down the numbers themselves, right? Break down the concept of 0, 1, 2, 3 all the way to infinity. So the next step, you see that I have odd and even, stating that you see 0, that's an even number, 1 is odd, 2 is even, 3 is odd, 4 is even, 5 is odd, 6 is even, 7 is odd, 8 is even, 9 is odd. So you see these 10 digits, right? These 10 numbers here, or units, I call them units. These 10 units, 0, 1, 2, 3, all the way to 9, they all are odd or even. They all 5 of them are odd, 5 of them are even in these units. As you can see in the second part, under that, the even numbers I have, which is 0, 2, 4, 6, 8, they're the smallest even number that includes all even numbers. So all the even number, or all the even units, the way we write it, we write 0, we write 2, we write 4, we write 6, we write 8, right? This is the smallest number that consists of all the even numbers, right? 0 is an even number, 2 is an even number, 4 is an even number, 6 is an even number, 8 is an even number. When you put them together, they create one big even number, a 5-digit even number. This is even. The next one is 1, 3, 5, 7, 9. They're all odd numbers, and all together they make a odd number. And they are the smallest odd number that includes all the odd numbers, or all the odd units that we use to write numbers with. And if you were to write something, let me make some space here. If you were to write 10, right after 9, right? 10, 10, which, as you can see, consists of a just put it like this. Which consists of a odd number and then an even number. Now 11 consists of an odd number and an odd number, because 1 is odd, and since there's 2 ones, they're both odds, right? When you put 12, you got a odd number, and then you got an even number, and it goes on and on and on and on. Let's go with a bigger number, right? 100, for example, consists of a odd and then 2 even numbers. Then if you go 101, that is odd, even, then odd. And then of course the next one will be 102, which would be odd, even. And then you can see a pattern after that, because the next one will be obviously odd, even, odd, And we already did that right here. We already did that with 101. 101 was already odd, even, odd. Just like 100 is odd, even, even, but 102 is also odd, even, even. Since that happens a lot in multiples, interesting fact, it's in multiples of tens. So in multiples of 10, every 10 digits, 10, 20, 30, 40, 50, 60, a billion, a trillion, a gajillion, infinity, right? You will get these repetitive patterns of odd, even, right? Odd, even, odd, even, odd, even, odd, and even, odd, even, you know, or odd, even, and so forth and so forth. Now, will there be a number that is just odd numbers? Because, you know, odd is the only time you 3n+1, right? 3 times the odd number plus 1, and that's the only time you'll be able to go towards infinity. It will never be whenever the number is even, because you always go down to 1, or you always will divide by 2, which means you are going the opposite direction. The goal is to try to go to infinity with 3n+1, right? So you want odd numbers to constantly keep popping up. So what number times 3 plus 1 will always create an odd number? The thing is, I mentioned before in my previous video, was the fact that the only difference between an odd number and an even number, the differential, is 1. The difference between the number 1 and the number 2 is 1. The difference between 2 and 3 is 1. Now you might like to think, all right, well, what about this? The difference between 1 and 5 is 4. And it's like, okay, if you put it that way, it does sound like, oh, okay, it's not always 1. The difference is not always 1. When you use those, you know, when you say those two numbers, but notice that those two numbers are both odd numbers, right? I'm saying the difference between a odd number and an even number, the difference is 1. Yeah, it only takes 1. From what I've seen so far, it only takes 1. Because let's go with the next thing, which is, here's a really big number that consists of just one odd, right? I'll use the number 1. That's an odd number. And then throw a whole bunch of zeros behind it, which are even, right? I could just keep going. I hold it, right? I just keep on going to infinity and beyond. That's a pretty big number, and it just keeps getting bigger and bigger and bigger. So I just keep adding a 0 to the end, right? Regardless of how many zeros I add to it, it doesn't matter. Why? Let me go back. Because there's a 1 in there, right? The 1 is odd. No matter how many evens, aka zeros, I put in there, there's a 1. Now you could be like, all right, well, give me another number. All right, well, I'll give you 2, right? 2 to infinity, right? Which is an even number, which is bigger than 1. That's important, right? 0, you can say, oh, well, that's less than 1. All right, cool. Then we'll go 2. 2 is bigger than 1. So we still have 1, which is odd, and then all these 2's that are bigger than 1. All these big 2's, but they're all even. Yet, there's still that 1 odd. That 1 odd makes a drastic difference. That 1 odd at any point could multiply, right? Let's take this number down to a smaller number. Let's punch it in, right? Let's make it a 5-digit number. Let's go with 5. That seems, no, let's go with 10. All right, so that's 5. So I just need 5 more. 1, 2, 3, 4, 5. All right, 10 digits. 10 digits starting with 1 and 2. Now we have the Collatz Conjecture calculator here from mathcelebrities.com. Click on it. Normally I use some of my phone or the other laptop, so it'd be faster. Obviously this is my slow computer, so it'll be a little awkward. It's going to take a while, longer than expected. Let's see why it's taking longer than I expected to. Could be just the browser that I'm using. Oh, looks like it did something. Alright, cool, it processed what I wanted. Yeah, the browser is a lot slower than expected. Alright, normally I use Firefox, but right now I'm using Edge, Microsoft Edge, whatever. Alright, so let's see how many steps did it take before we look at anything else. So that 10-digit number, which is pretty big, it consists of a lot of even numbers. So it took 232 steps to get to 1. Alright, well, it got to 1, so that's an important detail, right? It got to 1. And let's see, let's go back to the top and see what happened at the first step. So the first step, as we can see, even though there was a 1 in there and all these 2's, is classified as an even number. So right off the bat, it was going to be divided by 2. So it's already going towards 1 by default. But then, when it was divided in half, it became an odd number, which means you had to start going towards infinity, right? You had to go back up. Then it became an even number. Right here, see? It became an even number. Then it became an odd number. Then an even number. Then where am I at? Then it became an odd number, even, odd, even, odd, even, odd, even, odd, even. I'm hearing a lot of evens. Odd, even. And of course, it keeps going even. It got to 1 odd, even, then odd again. But then it went even, odd, odd, even, odd, even, odd, even, odd, even, got to odd, even, 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 odd, even. And eventually, I think it's once it gets to 100 steps, you just start seeing a lot of evens. There's some more odds in there. Clearly this goes on for a long while. I guess it's when it passes, what was it, 200? Let's see, past 200. Let's see what happens once it passes 200. Right, so once it gets to the 200th step, it's even, odd, even, odd, even, odd, even, odd, even, odd, 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 even, odd, even. Yep. And now it gets to 232. It gets down to 1. And you heard me say even way too many times. Way more than you heard odds. Now, there might be an interesting possibility. This is why I was trying to come up with a method that could say that they could say that the conjecture, you know, would be untrue. Would be a scenario where half of infinity, right? The first half of infinity will always go down to 1 because all those numbers, you know, is a combination of odds and evens, more evens than odds, as you can see, because every time you do the math, you know, it just keeps on going odd, even, odds, even, odds, even, odds, even, odd. You hear evens a lot. Obviously, in order to go back down to 1, you have to hear evens a lot. Even has to happen constantly in order to go back down to 1. So then the other half of infinity, in order to reach infinity, right, to get to infinity, it would have to be a lot of odd numbers that direction. That means odd has to happen more often than even in order to go towards infinity. So in this scenario, that's why I was like, yeah, with the fact that we're dealing with infinity, let's go back to my thing. The idea of going into infinity, so that I guess that'll bring us to the next section, to infinity. Let's save this. Right. To go to infinity, because infinity or infinite is both odd and even. It's both an odd number and an even number, mainly because it consists of 50% odd numbers and 50% even numbers. That's the assumption anyway. High possibility that it is, because so far pattern wise you see that for every odd number there's an even number, especially if you go with the specific example I use of these even numbers and then these odd numbers, and they're use these units, these symbols, 1, 3, 5, 7, 9, 0, 2, 4, 6, 8. These symbols are constantly used over and over and over again when you're, you know, counting, when you're, you know, doing math and you're doing this conjecture, always punching in as the biggest numbers you can come up with using these specific units, these symbols. Since these repeat, and you have again 5 digits that are even, 5 symbols that are even, and 5 symbols that are odd, there's infinite combinations that you can use these odd and even numbers. You know, let's go back to the conjecture right quick. Let me copy this odd, right? Because the idea is that we're trying to go to the part of infinity which is close to infinity, further, the furthest, we're trying to get the furthest away from 1 as possible, right? Because we don't want to go down to 1, right? The idea is to go to infinite, not go down to 1, because then if, you know, we always go down to 1, then the conjecture is true. The idea is we're trying to prove that it doesn't always go down to 1. We have to get the furthest away from 1 as possible to greatly increase our chances of just going to infinity and never coming back. But I believe you will always come back. It's just inevitable, but however way you pronounce it. Alright, so okay, I showed you the even variance of this. Let's show the odd. I was going to do something else, but it's fair to show. Is this even working? It doesn't seem like it's loading, so let me restart that. Okay, that's not working. You know what? Oops, what happened there? Alright, so let's punch that in here. Oops, that was the wrong thing. Go back to here. Let's grab this. Open that. That's really annoying that that's not working. This one should. Yep. Don't need this thing to not be working right now. Come on. Work for me. Give me what I need. I'm trying to grab the number again. Because we did even the even numbers, or the smallest of the biggest, or the biggest smallest even number. Now it's time to do odds. So what was it, 100 and something like that? I forgot. We can check afterwards. I forgot how many steps the even numbers were, but let's see how many steps the odd numbers are. So let's scroll down to the bottom. Alright, so it's 37 steps. So what was, how many steps was the other one? I could just punch in the numbers 0, 2, 4, 6, 8. Alright, let's see. So this one. Alright, so okay, so 133 steps for even numbers only, and all the even numbers, or all the even units. Let's punch the odds again. So 131 was it, and now we do this, and this was like 32 if I'm right. Oh yeah, let me exit, right, let me stop that for a second. Notice that when I did put the these right here, the 0, 2, 4, 6, 8, you notice that 1 is an even number, obviously, right? Because it only consists of even numbers, and this whole number is even. So obviously it was even, so it would be divided by 2. But once it got divided by 2, it became 1,234, which is half of that, right? Which is 1, 2, 3, 4. Isn't that interesting? Which is a odd, even number. It started off as even, but then it turned into a, well, actually, technically, the 0 is in front of the 1, so it's 0, 1, 2, 3, 4. So it's even, odd, even, 5 digits. But for the rest of the stuff, obviously, 0 is carried in front of all this stuff. It just, you don't see it because it wasn't portrayed there, but 0 is in front of all these numbers. Anyway, the point is, it's interesting that you immediately get 1, 2, 3, 4, or 0, 1, 2, 3, 4. Right, which is interesting. And this has one, so this has 1, 2, 3, because you count the 0, 3 even numbers and 2 odd numbers. So 3 evens, 2 odds, still equal, as you can see right here, still equal an even number. So you take all these even numbers, divide them by 2, and you still got an even number. So you're going to have to divide it by 2 again, which now becomes 617, which, as you can see, is an even number followed by 2 odd numbers, which makes it odd. So the pattern you're seeing there is that the number, if the number has more even numbers, it's an even number. If it has more odd numbers, or if it has more even digits in the number, it's an even number. If it has more odd digits, I mean units, not digits, units, if it has more odd units, then it's an odd number. So the fact that this has 2 odds and 1 even, it's an odd number. Therefore, you have to do the math to try to go to infinity, right? But then once you do, it becomes 1852, which happens to be even, because 8 and 2 are even numbers, 1 and 5 are odd. Notice that this isn't more, they're actually even. There's 2 odds, 2 evens. That seems interesting, right? But still it turns out to be even. So tools where the number is even. And right here we have another number. Once you divide by 2, you still get another even number, which is 9, 2, 6, because the 2 and the 6 are even. The 9 is odd, but since there's more evens than odd, then it becomes an even number, and you just keep on going. And then you see, obviously, this just kept going up and down, up and down, up and down, up and down, up and down. A lot of evens, very few odds, but a lot of evens. Even at the end, it just went from even, odd, and then just went even, 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 all the way down to 1, right? Obviously. And again, this took more steps. Took more steps. So to get back down to 1, it takes more steps through even numbers than it does through odd numbers. But it implies that any combination of numbers you have, combinations of 1, 2, 3, 4, 5, 6, 7, right, 9, you will always end up with something that has more that has either more odd than even, or it becomes even when it's even, if that makes sense, right? When you have something that's both odd and even, it turns out to be even. So a number that's both odd and even, or equal amount of odd units and even units, it's even. If it has more even units than odd, it's even. But if it has more odds than even, then it's odd. So there's something to play with, something to conjecture, right? Something to think about. So we did that. So you see that the even number, right? Let me go back for a second. What was I saying? So which one is this one? This one was the... Oh wait, that was that. No, wait, where am I at? I'm totally somewhere else. Okay, this is where I'm supposed to be at. All right. So this is okay. So when I used the even numbers, it gave me over 100 steps. All right. So it was more steps when the number was even. Now let's go back to the odd number. So when it's an odd number, it should be a totally different thing. Let's copy that right quick. Hate that this is not acting right. Come on. There we go. Man. Soon I won't be using this computer anymore, and I'll use my Windows 10 instead. This is Windows 7. Alright. So what was that? So we got the odd numbers, just straight odds. And as soon as you multiply it by 3 and add the 1, it becomes even, and then it becomes odd, then even, even, odd, even, 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 odd, even, even, odd, even, even, odd, even, odd, even, 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 odd, even, 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 even. 37 steps, and it gets down to 1. So even numbers, whenever they pop up, will drastically take a big step back, from wherever position it was in, way closer to 1. You know, it likes 1. Why not? 1 is pretty cool, considering that 1,350. I'll just say 13,579 consists of 13,579 ones. The number 1 is in here 13,579 times, because if you divide this by 1, you get 13,579. That's how many ones are in there. How many 1 of the 1 unit, right? So that's why when you add 1, you go from a odd number to an even number, right? Notice that this is an odd number, right? So obviously, because all the numbers here are odd, but then when it got multiplied by 3, it became 40,737, which consists of 2 odds, then an even. 2 evens, then an odd, then another odd. All right, so it's 2 evens and then 3 odds. Now here, there's more odds numbers, right? The 7, the 3, and the 7. That's more than the even numbers. So then this is an odd number. But then you add 1, which means you're turning this 7, which is currently an odd number, into an even number. So now you got 4, 0, those are even numbers. 7, 3, those are odd numbers. And then you have an 8, which is an even number. So now you got 4, 0, 8, which are 3 even numbers, and only 2, 7, and 3 are the odd numbers. Since there's more even numbers than there are odd numbers, obviously this is a even number. But if this turned out to have the same amount of even numbers, and odd numbers, then it would be even. It would turn out even, because if they're the same, if they're 50% of the number consists of odd units and 50% of it consists of even units, then it's even. I don't know, that's just the way it is. I'm just letting you know how these things work. Just pointing out an observation. So it seems really interesting, right? So infinity consists of both odd and even numbers, about 50% of odd, 50% even. Now, could that be wrong? Right? Could that be wrong? That's 50-50. That's an even split. Based off of what I just was discussing, it seems more like there's more even than odds. So let's break this down to, it seems like a 2-3 ratio. So I'll go down to what will be a 2-3, basically 5, 2, 3, 5, 6, 40. Yeah, it would be 40, right? 40 and 60. So yeah, pretty much like that. So shift over to, because half of 40 would be 20, half of 60 would be 30, so that's the 2-3 ratio I was thinking of. As in 2 odds versus 3 evens, since 3 evens outnumbers 2 odds in a 5-digit sequence, in a 5-digit number, for example, that number turns out to be even instead of odds. So and then of course, since we're doing percentages here, I take the 20 times it by 2, blah blah blah, you get 40 for it, because we're trying to do a 100%. So 40% of infinity is odd numbers, and the remaining percentage of infinity is 60%. Of infinity is even numbers. So with that viewpoint, let me save that for now. With that viewpoint, you know, or with this idea, if that's the case, because if it's 50-50, then there's a higher chance that there is a number that as soon as you multiply by 3, it will just immediately shoot up to infinity, and like it will immediately be infinity plus something, like plus 1,000 or something, and beyond. You know, like you just go to infinity and beyond, right? So it might not come back down to 1, or if it does, it just takes a lot longer. My belief is that it just takes more. It takes more than infinite to come back. It takes multiples of infinity. It takes infinite infinites, if that makes sense, to come back down to 1. Like the steps, going from infinity down to 1 takes more infinite steps than infinity, right? Let's go with a hypothetical of the let's just use a number to represent infinity, 100, right? Counting from 1 to 100 is just 100 steps, right? 1, 2, 3, all the way up to 100. That's 100 steps. But with the Collatz Conjecture, when you start doing that and go back, we can actually use the calculator, obviously, right? And let's just punch in 100. So if we put in 100 to Collatz Conjecture, how many steps back does it take? Does it take 100 steps? You would like to think it would, right? You would like to think, because it's like, if it takes 100 steps to go from 1 to 100, it should take the same amount to go back. Or maybe double, you know, since it should take less, right? Since whenever an even number comes up, we should always be able to go back. Where am I? Oh snap! I was on the wrong web browser. You know, I really should just close that one, since this is not working. All right, so let's do that. 100. So if it takes 100 steps to go to 100, if you get even a lot of between 1 to 100, if there's a lot of evens numbers between 1 and 100, then, and you keep landing on even numbers, you'll go back to 1. So then, because when you think of dividing by 2, you might think that it'll be 50 steps. Like it'll be less than this number. So 50 steps. Why is this taking longer than it should? Hate that this is doing that. Trying to do something here. Just exit out that one. Let me open up another tab. Try that again. Come on. There we go. One of y'all have to work. Alright. It's the first one. Good. Alright. So, we put in 100. It's an even number. It's already divided by 2, which gives us another even number. Which notice that 50, which is, it's a 5. 5 is odd, 0 is even, but it's still, you know, it's an even number because there's an even number, right, of odd and even units. 5 is 1 odd unit and 0 is 1 even unit. So it turns out to be even divided by 2. Now you have a even number, which is 2, and 5 is odd number, so you still have a scenario where both numbers are both they're both the opposite, you know, odd and even, so equal amount of the same units. But as you can see here, the 2 and the 5 is odd. Now here with the 50 you have odd followed by a even number. So odd before even. Here you have even before odd. So that's something to take into account, because that's a factor. Because they're both even, so it's like how do you differentiate? I'm having trouble saying words. The way you tell these, the way you separate these, right? The way you categorize these. That's what I want to say. Why 50 is even and why 25 is odd, even though they consist of the same amount of odd and even units, is because the positioning you have. So in this scenario, since there are equal amounts of odd and evens, you have to take into account the position, what's in front, what's in back, right? So if odd is in the front and even is in the back, if you want to look at it that way, front and back, the beginning and the end, since even is in the beginning and odd is at the end, then it turns out to be even. But here, if you have even in the front and odd at the back, then it turns out to be odd, right? So it's more of, the best way to put it is whatever's at the back is the deciding factor. So the last number is even, so the number is even. The last number here is odd, so it's odd. That's a way of looking at it. That's a rule of thumb. And then right here we got 7, 6, which is 7 is odd, 6 is even. Since it's at the end, it's even. 38, which is odd and even, but at the end is even, so it's even. So there we go. We're seeing a pattern there, right? 19, which are both odds, and odd is at the end, odd is at the beginning, which might be irrelevant. The fact that it's odd is only odd. It has no choice but to be odd, because there's no even to even change it to anything else. It's automatically odd. You multiply it, but then what, and then add, which, so here's an odd number. When you multiply it by 3, it becomes another odd number. It consists of 2 odd numbers, 5 and 7, but you add 1, turning the 7 to 8. And since the 8 is now is an even number, and it's at the end of this number 5, you know, at the end of this number, number 58, it becomes even, so you have to divide. It becomes 29, which is odd, so you start multiplying, going back up to 87, which is an even odd. So of course that would be an odd number, but then add 1, now it becomes a 8, which is 2 even numbers. Obviously, since there's 2 even numbers, are automatically going to be even, so you have to divide them by 2. They become 44, which is another even number. You divide by 2, which becomes 22 even number, so you divide again, they become 11, which now is odd. Now we have an odd number. 1 is odd, times it by 3, it becomes 33, which is an another odd number, but then add 1, so it becomes 3, 4. Odd, even is at the end, so it's an even number, so you have to divide it by 2, it becomes 17, then it becomes 51 plus 1, so it's 52, which is odd, even, odd, even, odd, even, and even, right? It just goes, once it gets to 16, it'll be like 16, 8, 4, 2, 1, obviously, right? So how did it get there? It got there by, so when it was 34, it became 17, 52, 26, 13, and then 40. Once it hit 40, that was too easy. So once it hit 40, it was like 40, 20, 10. Half of 10 is 5, so that's an odd number. So here is 40, 20, 10, which is even, because here, see, 40 is both even numbers, 20 both even numbers. But here is an odd even, but since the last number, the last unit is 0 in this number, so it's even. So it becomes an even number. Divide that by 2. Now it becomes a 5. 5 by itself is a odd number. But if you want to think of 5 having 0 in front of it, which is an even number, it's still it's even odd, and the last number in that 0, 5 configuration, 5 is odd, so it's an odd number, obviously. So you're gonna have to multiply. It becomes 15, which is an odd number. Add 1, it becomes 16. So 6 is an even number. 1 is odd, since 6 is at the end. Obviously, it's an even number. So you divide it by 2, which gets you to 16. Which will get you to 8, which is even. Divided by 2, which is 4. Another even, 2, another even, divide that by 2, breaks the 2 down to 1, and 1 is the magic number. And it only took 25 steps to go from 100. 25 steps. So out of 100, instead of 50, like I said, 50 steps, it took 25 steps. Right? So let's see if 100 is 25 steps. Let's see if 1,000 is 50 steps. Is 1,050 steps, or is 250 steps? So then 1,000 would be 100 steps. So let's see if 1,000 is 100 steps. Okay. Let's see. Scroll down. Let's see. Oh, I see 100 steps. Okay, 111 steps. That's interesting. So by what I was trying to say. All right, so we got, out of 100, we got 25 steps, which is 1/4 of 100, or 25% of 100. So 25% of 100 is 25%. I mean, it's 25. So 20. So let's bring up a calculator, because I'm curious. What's 25% out of 1,000? Do I even know how to do percent in here? 25, the percent symbol. That didn't work out. Okay, so I want 1,000, right? And the idea is to divide it. Is that? Do you divide? Divide by. What was the number again? Was it 25%? Yeah, 25%. I don't know how to use percentage in here. Let me see. Hit that. It gives me a 4. That don't even make sense. All right. Yeah, I don't know how to do percents on this calculator apparently. Let me see. 1,000%. That didn't even make sense. Because when do you put the percent? Where's the percent supposed to go? 25%? Okay, since I'm trying to divide, let me see. 1,000 divided. No, I did that already, right? 1,000 divided by 25. And I hit percent, which for some reason gave me 250, or 250 popped up, but it's like, that makes sense. Oh, I'm trying to divide, isn't it? I'm trying to subtract. I do not know how to do percents. My bad. I think you do decimals or something for percentage. Anyway, the point is, I'm gonna go with an assumption. So we got 25 steps out of 100. Right, 100. Okay, so divide 100 into 1,000. Let's see if that will work. So 100 into 1,000, would it be 100? It'd be 100, but then how you get the extra 11 though? So 1,000 divided by 100 it's 10. All right, 10. Okay, 10. Okay, 10 times 25. 10 times 25. Which, okay, so it was 250. Okay, but how do you get from 250 though to 111 steps? Well, the interesting fact, well, right here it proves one thing though. The bigger the number you choose, the smaller the steps are. Because there was a number, because I was watching a video about Collatz Conjecture, obviously, and they show like one of the biggest numbers has like 953 steps, but it's a huge number. It's in the billions. It's a number that's in the billions. Yet the number of steps it takes to go from that number, that billion plus number, to 1, and it does go to 1, that's less than 1,000 steps. Which, think about it, that's fractions. That's a small percentage of the numbers. Think about it. It takes more steps to get to that big number, going 1, 2, 3, 4, 5 to a billion, than it does to go from a billion, do the Collatz Conjecture, back down to 1. So to go back down to 1, it takes a lot less steps than it does to go up there. Now granted, it's because you're jumping, right? You're jumping around in taking big steps, like hopscotch, taking big steps forward, big steps backwards, but you're taking more steps back than you are forward, if that makes any sense. Because half of 1,000 is 500, for example, right? 500. Then you take that 500, times it by, so let's do it, right? So 500 times 3 is 500 more than the 1,000 that you started off with. But then you divide that by 2. Now it's 750, which is about 75%. No, it's 25% less than what you start off with, which was 1,000, right? So it's 250 less than you started off with. Then times that by 3, bang, and then divide by 2, bang. So a little over 1,000 times 3, bang, divided by 2, bang. Okay, that's an interesting number. Then times 3 divided by 2. See, now we're getting to decimals, so we already know that this is going the wrong direction, because this needs to be whole numbers. These are not whole numbers, so that ended up getting messed up there. So again, 500 times 3, right, plus 1. Let's throw in the 1 and see how that works out. Then divide that by 2. We do get a 0.5, so that never looks good. Let's see, divide that, and then we're there because we divided. But of course, I'm not using the conjecture. I'm just multiplying and then dividing, multiplying, dividing. But obviously, with the conjecture doesn't just go multiply a number, then divide it by 2, right? Then multiply by 3 plus 1, then divide by. Since you're not constantly going back and forth between the first conjecture and the second one, there's a time where you keep going with divide, and then add. I mean, multiply. But then you can, divide. So you get the idea right there. But from what I see is the closer you are to 0, the more divide you do, the more even, the more divide by 2, then the further away you are from 1, you know, the closer you get to infinity, the more odd, the more 3 plus n, or the more 3 times a number, a odd number, obviously 3 times an odd number plus 1, because you're trying to go further, right? You're trying to move one step more towards infinity. But if it ends up being an even number, then you're drastically taking big steps back times, you know, divided by 2. And that's the real thing you're competing with. You're competing with the fact that when you divide by 2, you're taking way more steps back than you are taking forward, because you're besides, you know, times 3, which, you know, is a lot of steps forward, plus 1, but that 1 is what causes you to even take half of those 3 times steps you took, you know, back. And at any point when you go back, you end up even again. Then you're taking another half, right, of the steps you took back. So you're going back twice than you are moving forward. It's all because of that plus 1. Now, if you never had the plus 1, then you just be 3 times 3 times 3 times 3 times 3 times to infinity. But because there is a plus 1, any combination of an odd number, once you add the 1 to it, it will drastically change it to an even number. And that's all it takes, is just that one differential, that one step, for you to go all the way back to 1, back to square 1, as they say in board games. Alright, what else do I have before this video is over? Because I think I talked enough. You know, there's the negative infinity, blah blah blah, which obviously the percentage there will be different, because the interesting thing is that we're not starting the interesting thing is that we're not starting the conjecture from infinity, right? Infinity is essentially the end. It's where we're trying to get to, but we start off at 1, 2, 3, 4, 5, all the way up to infinity, right? So since we're way closer to 1, because we start off way closer to 1, the percentage, the high mathematical percentage of even numbers popping up more than odd numbers are a lot higher, closer to 1. Closer to infinity, the odd number it probably flips, and the odd numbers outweigh the even numbers. But there's still even numbers on that side nonetheless. They're just a lot less predominant. They're like, there's more odds than even on that side, closer to infinity. Because that's the way you keep counting. You're counting going from, because think about it, if 0 is even, in order to go towards infinity, you got to add 1, right, which gets you to 1. So 0 plus 1 is 1. Since 1 is odd, right, 1 is odd. And think about that, even plus 1 is an odd number, times 3 is also an odd number, 3 is an odd number. 2, when you divide by 2, that's an even number. So that's why it's interesting that when a number is even, you divide it by 2, which is also an even number, or even unit, I should say, even unit. 3 plus n plus 1, right? Those are 3 and the 1 are odd units. So whenever you got an odd number, you use these odd units to, you know, to do the math. 3n plus 1 for that odd number. But because that plus 1, that odd number, right, that plus 1, that odd unit, can turn a odd number it can't turn to another even number, but once you add 1, eventually you'll hit a even number. You'll turn a odd number into an even number eventually, which will drastically send you back a whole bunch of steps, and then forward, back, and just keep yo-yoing until you eventually come back down to 1. Now, I just thought of it right now, because what I was saying will be interesting, that from 0 to half of infinity, once you get to half of infinity, let's go with that idea, right? Half of infinity, half of infinite. What if there, at that point, is where you just keep, every time you do the Collatz Conjecture, you just go, you go from odd to even to odd to even to odd, and just go up and down in a wave pattern, a sine pattern, whatever pattern, up and down. I'm trying to illustrate the up and down. What is it? This, up and down. I did it wrong somewhere. You get the idea. You get this type of like frequency. So you go up, down. I guess I'll save that. Up, down. Oh, did one part wrong. That part. There you go. That looks even, and that's the important. Even. So far, it seems like infinity is not even per se, because again, closer to 1, there's more even numbers than odd numbers. When it comes to the conjecture, how even pops up a lot, which is why you get down to 1. If odd popped up more, you will be multiplying by 3. Therefore, you will go, you'll go towards infinity more often, which is why I say, closer to 1, more even. Closer to infinity, probably more odds. But in the middle, right, there has to be a middle ground. In the middle of infinite, it's an equal amount of odd and even. So we can go here and just go 50-50, because if it's 50-50, right, if it's 50-50 chance, right, we'll go with that idea. If it's 50-50, 50 even, 50 odds, an equal amount of odds and evens, then this will just keep on going. It'll keep trying to go to infinity, but it'll also keep trying to go to 1, but it'll also keep trying to go to infinity and keep trying to go to 1. Pretty much a paradox. So there's that. So maybe that could be something of interest that people can toy with, the idea of like, okay, yeah, what if we can figure out somewhere in the middle of infinite? As you can see down here on the bottom, the last part, trying to find the smallest percentage of infinite to use in the Collatz Conjecture. As you can see here, I try to make a little infinite symbol, right? Infinity divided by 2, which is 0.5, half of infinite, right? Half of infinity. Then times it by 3 plus 1. But this is assuming that half of infinity is an odd number. So then you'll times it by 3 plus 1 equals 1.5 or 1.5 infinite, and 1, obviously, because you added the 1 at the end, and 1, which is more than 150.1%. This percentage might be a little inaccurate. It's probably like 0.00000, right, 1, but I don't know. Right there, I'm assuming. I'm just something I'm toying around with, the idea, because infinite, conceptually will be considered a huge number, even though the concept of infinite is a concept, not an actual number. Infinite's not a number, but it's the idea that something just keeps on going, and there's almost no end to it, or there is no end. But because this conjecture has to do with numbers in general and the idea of infinity, you know, just like, because unless you can prove there's like, no, there is a finite number. Here's the thing. For me personally, if there is a number, like a big number, like a huge number, the size of 10%, the number is the size of 10% of our known universe, it still will consist of odd and even numbers, right? For all we know, that 10% number of the universe, whatever I was just saying, will probably be an even number. So then you have to divide it by 2 right off the bat. So half of that 10%, you know, and then it might be an odd number. So yeah, you multiply it by 3 plus 1, but then it might reach another, again, it'll hit another even number. So you divide it in half again. It might hit another even number after that, divide again, and so forth and so forth. It's going to take a long time, but it will do it. That's the thing. We notice that the bigger the number, so far we've seen the bigger the number, the less steps there are. And I want to do one more thing. So that was one more thing. Let's see. 1, 3, 5. Okay, it's right there. All right. I want to look at the number of steps again. The number of steps. Because ultimately, when it comes to proving the conjecture wrong, the Collatz conjecture wrong, it's about finding the biggest odd number, the biggest odd number you can possibly come up with. That as soon as you times it by 3 plus 1, you know, it goes to infinity essentially, and it keeps becoming odd, because it's implying that up there, that high up in infinite, for example, is more odd. Well, you want to hope it is. If the expression, I like using this expression, as it is above, as it is below, it is as above, or as it is above is as below, right? Well, no, it is below as above. So if at the smallest scale the conjecture works, then at the biggest scale it should also work, especially when the biggest scale consists of the same fundamentals as the small scale. It's just more of it, right? Like a adult and a child are relatively the same. We're still human. It just, there's more human in me than the child. Like there's more atoms in my body than there is in the child. The child has lesser atoms than me. Or we can just say their atoms are more condensed than mine. Maybe we have the same amount, right? Maybe we're even. Me and a newborn baby, and I'm a big guy, I'm over 300 pounds, we're equal when it comes to atoms, but the child is more condensed than I am. So the child has 300 plus pounds worth of like atoms, as it were, per se, whatever that means, right? But it's condensed. The older they get, they're actually expanding the atoms. Same amount of atoms, just that by the time they get my age and they're 300 plus pounds, you know, then we're the same. But we were always the same. It's just that, you know, they were condensed. I'm expanded, very expanded, over 300 pounds. So, like I was saying, this number here is just nothing but odds, and it's 5 digits, and this nothing but odds, and that's what you're looking for, is a big odd number, because that's how you multiply by 3. You don't want even numbers, because you know that's just divide by 2, divide by 2, divide by 2, divide by 2, which, you know, the closer you get to 1, it's all about divide by 2, and you're trying to get away from that. Dividing by 2 or even numbers is your enemy. If you're trying to prove the Collatz conjecture wrong, you don't want it to be even, you want it to be odd, and nothing but odd. But here, 37 steps just for odd. It took 37 steps for odd. Which seems interesting, right? But then when you put even, 0, 2, 4, 6, 8, when you put the even numbers, when you put the even numbers, it took way more steps. Is because automatically the even number wants to become odd, which means you start going up really fast to through multiplication, but then eventually once you get back to even again, you're trying even again, you're going right back down, and eventually even wins. So you can see this is the even numbers, the even numbers, and they are 131, was it? No, 133 steps. So what was it? 131. Why do I keep forgetting this basic number? 131 versus 37. So that's an interesting thing. They're the same digits per se, but why was 1? Well, a way of looking at it is that the odd numbers were bigger, right? Let's look at it this way. All right. Yeah, because if you take out the 0, right? Let's say the 0 is not there, then it's 2,468 versus 13,579. So if you look at it that way, so the odd number seems to be a little bit bigger. So what would happen if I put the 0 at the end of that? Let's see if that changes the steps, because that might be the reason why we're getting that, because you want to believe the steps are the same, so maybe that's where it is. My mistake is putting the 0 in front of the 2 instead of behind the 8. So that's where I should put it. The proper position for 0 should be after the 8 in this process. Let's see. I'm human. I could make a mistake. Let's see if what's important is once you realize the mistake, right? Or that's always important. It's better that you realize your mistake before somebody else does. You know what I mean? Because then it gives you time to correct it and whatnot, and better improve your processes. Yeah, this looks like there's gonna be a problem. Oh no, it worked out. All right, cool. So let's see how many steps this is once you add the 0 to the end. Okay. So 38. The other one was 37. Because originally when we put the 0 in the front, it gave us a much bigger number, much bigger steps. The reason why it gave us much bigger steps, okay, that's why. All right, just one step more, so it's almost even. All right, because nope, this one's 38, so this number is 38, while the other number, all right, so let's put it right here. So this gives us, we put it this way, this gives us 38 steps, and then this one gives us, that's why it's important to write things down, 33 steps. So that's important to save that. So when we put it this way, because this is essentially 24,680, while this is 13,579. So there's that. But as you can see, there's 5 more steps when it comes to even numbers than when it comes to odd numbers. per se, but the real thing here is that 24,000 is way bigger than 13,000, and we've seen that the bigger, well, I said earlier, the bigger the number, the less steps it takes, right? That's what I said. The bigger the number, the less steps. Yeah, the bigger the number, the less steps it takes to get down to 1. Let's see. What number can I put here? Okay, I could put 3. Alright, so let's try 3. Let's take this and put 3. Just one last thing before I end this video, because this is essentially the end of the video. It's just, you know, it's fun, right? Math. Gotta have some fun. So let's make this number a little bit bigger. So let's make it to 3. Gotta keep it odd. I was thinking of putting 2, but I was like, no, that adds a even number to that sequence, and that will just mess up the idea. What we want to see is a big number, because 13,000 something, 579 is way smaller than the 24,680. So we want to see if this number right here, turning the 1 to a 3, because the next number after 1, it's not going to be 2. The next number that's odd after 1 is 3. So obviously turn the 1 to 3, and let's see if 33,000 something, how many steps that is. Let's grab this again, because apparently this wants to act up. Math celebrity, come on calculator. Let's put the number here. Okay, that's not working. Let's grab this. Okay. Let's punch that in there. So let's put 3,579. Let's exit out of that one. Grab that. Yeah, this is really annoying that this is acting up, because normally it doesn't do this. Normally it just works fine. I get to do a lot of stuff on the computer, but now it wants to act funny. Why? Because I'm recording. There we go. Finally wants to do something. Alright, let's see, what did I get? How many steps? I got 67 of 33 times 2 is 66, so it doubled. Once I turned this to a 3, it doubled the amount of steps. Stuff to take into account, stuff to think about. But at the current time, this is what you got. 38 steps to go from this even number, and 33 steps to 1 from this odd number. See, now the steps I was saying about, the bigger the number, the smaller the steps. Smaller in comparison to the big number. I'm not saying smaller in general, where if you take a billion, right, or a trillion. Let's say a trillion is a even number, so you divide that by 2. That's half a trillion. That's still a big number, right? Obviously, right? But let's say that's another even number, so you divide it by 2, half of that. Still a big number, but it'll still take a long time for it to get to 1, obviously. So the amount of steps it will take will drastically change when you divide by 2. It'll be interesting if infinite being both odd and even, an equal amount of odd and even, and more likely it would infinite will be a even number. Let's just go with the idea that it's an even number in a way, like even in the sense of, you know, the conjecture. Then you would divide that by 2, so then half of infinity, and then if half of infinity is also even, then half again, and half again, half again, half again, and keep going until you finally get down to 1 or something similar. But we shall see. And that'll be the end of the video.